Chapter 9 is all about hypothesis testing with one sample. So in this chapter, we're going to learn how to test claims about means and proportions. We'll see the relationship between confidence intervals from our last chapter and hypothesis testing in this chapter. We will understand the limitations of hypothesis testing and how errors can occur. And this chapter just allows us to test claims with one sample means or one sample proportions. And this is where our fun really begins with our inferential statistics. So one of the jobs of the statistician, as we talked about last chapter, is making inferences about populations based on samples. And confidence intervals, which we did last chapter, was just one of many ways that we can do this. This chapter, we're talking about hypothesis testing, which is another way that we can make inferences. So we're able to make a claim and then test to see if that claim was true or not. And this is called hypothesis testing. Now, the process that you go through for hypothesis testing, which all of you will go through as you do your project for this class, there's 6 basic steps for if you're going to go out in the field and make a claim, collect data, and test it. So the first step is to set up 2 contradictory hypotheses. So you're saying, this is what I claim, and these are 2 things that contradict each other, one of which is my claim. And then you're going to design a study to be able to gather data to actually test it. So you're designing your study, whether it's an experiment or just observations, you're designing that. You're figuring out how you're going to collect your data, all of that stuff, going back to your first few chapters of this class. Now, step number 3, you're actually collecting your data. So you're going through and you're following that process that you set up when you designed your study. Step 4, you're kind of determining which distribution is the correct distribution for performing your hypothesis test. And so like right now we have our student t distribution and we have our standard normal distribution. Those are our only choices. In later chapters, as we continue to do hypothesis testing, we will see that there are other options that we might use, but for now we just have those 2 distributions to choose between. The 5th thing is you're analyzing your data by performing calculations based on your distribution, and that will ultimately allow you to either reject or not reject the null hypothesis. And then we make a decision based on our calculations and rejecting or not rejecting the null hypothesis, and we write a meaningful conclusion to go with it. And this meaningful conclusion is kind of what you are doing when you're presenting your information from your study. So these are the 6 steps that you're going to follow when you complete your research project in this class. Now, we're writing hypotheses and they should be contradictory hypotheses. So the first hypothesis that we're going to write, we're going to call the null hypothesis. The null hypothesis is a statement about the population parameter that is either believed to be true or is put forth as an argument unless it can be shown to be incorrect beyond a reasonable doubt. Then we have the alternative hypothesis, and it is a claim about the population that is contradictory to the null hypothesis, and it's what we conclude if we reject the null hypothesis. So we have a null hypothesis and an alternative hypothesis, and we can see our abbreviations for them here. Now, since they have to be contradictory and the null hypothesis is going to have to contain an equals part, what we're going to see is there's only a few sets of hypotheses that we could have. So we could have something called the 2-tailed test, where the null hypothesis is the mean is equal to some value. The alternative hypothesis is the mean is not equal to some value. A right-tailed test would be the null hypothesis is the mean is less than or equal to some value. Alternative hypothesis, the mean is greater than some value. And a left-tailed test, where the null hypothesis is the mean is greater than or equal to some value. The alternative hypothesis, the mean is less than some value. Now, there are only 2 decisions that can be made as a result of a hypothesis test. The first decision, we could reject the null hypothesis. The second decision is we could not reject the null hypothesis. These are the only 2 choices that we can make when we're making our decision. Now, we will talk later on about how we make these decisions, but these are the only 2 options that we have when we say that we are going to make a decision. Now, we're going to kind of get all of the different little pieces that we need for doing our hypothesis test, and then we will get to the hypothesis test. So bear with me a little bit, as it seems like things are just going to be thrown at you. So I'm throwing them at you in the most logical order that I can without us getting sidetracked on the different distributions that we might need. So we're thinking, okay, we have these 3 different sets of hypotheses that we could write. When I'm doing my test, I'm either going to make the decision of reject the null hypothesis or do not reject the null hypothesis. I always have a null hypothesis and an alternative hypothesis, and we need to make sure that we know how to write these hypotheses. So if we were trying to write the hypotheses, here's a few examples. So we want to test whether the mean GPA of students in American colleges is different than 2.0, and write the hypotheses. Okay, so we're comparing the mean to what number? To 2.0. And then we look and we say, okay, what keywords do we have running around here? Well, I see the keyword different. Different means not equals. So if I need a not equal somewhere in there, I would need a two-tailed test. I would need the null hypothesis is the mean is equal to 2.0. The alternative hypothesis, the mean is not equal to 2.0. If we wanted to test to see whether the mean height of 8th graders is more than 66 inches, we'd be saying, okay, what am I comparing the mean to? Comparing it to 66. Where's my word that's helping me determine what maybe my claim is here that can help me write this out? We're testing to see if it's more than 66. More than would be like greater than. So I would have here a right-tailed test. So I'd have the null hypothesis, the mean is less than or equal to 66. Alternative hypothesis, the mean is greater than 66. And the third one here, we want to test to see if college students take less than 5 years to graduate college. So we're comparing the mean to 5, and we're saying less than, so we would have a left-tailed test here. So the null hypothesis, the mean is greater or equal to 5. Alternative hypothesis, the mean is less than 5. Now for each of these, it might be good to identify what our claim is, because we're going to be writing our sentence about our claim when we get to writing our sentence. And in each of these, the alternative hypothesis is our claim, because we're claiming it's different from 2.0. We're claiming more than 66 inches. We're claiming less than 5 years. And so it's good to be in a practice of going ahead and writing which hypothesis is your claim. So just after that hypothesis, writing claim in parentheses so that you have it there for your reference. It's not something that you necessarily have to write down in order to be technically correct, but it's good practice to do when you're first learning. That way you're making sure that when you go to write your sentence about your claim, that you know which hypothesis is your claim. Now, when we're making our decision and we have these outcomes happening, we had 2 decisions. We could decide that we wanted to reject the null hypothesis, or we could decide that we didn't want to reject the null hypothesis. Now, we could choose to reject the null hypothesis, and it could have been that the null hypothesis was actually true, or that it was actually false, or we could have not rejected when it was actually true or when it was actually false. So we ended up with actually 4 different possible outcomes. So the first one that we're going to look at is the decision to not reject the null hypothesis when the null hypothesis is true. This would be a correct decision. If your null hypothesis is true, you would want to not reject it. Now, we're never going to really know if our null hypothesis is true or false. So we're not going to know the true value, the true state of nature. We will be able to know, what decision we make based on the data that we did collect. For this first possible outcome, we make a correct decision. There's no error involved here. In the second one, we could make the decision to reject the null hypothesis when the null hypothesis was true. This is going to give us something called a type 1 error. We made a wrong choice. Now, we don't know that we made a wrong choice, but we made a wrong choice here. Our third possible outcome, we could decide to not reject the null hypothesis when the null hypothesis was false. Now, this would be an incorrect decision to make. because if the null hypothesis was false, we would want to reject it. But we don't know the true state of the null hypothesis, whether it's true or false. And based on our data, we decided to not reject the null hypothesis. So this leads to an incorrect decision, which is known as a type 2 error. And then step 4, the decision to reject the null hypothesis when the null hypothesis is false. This is a correct decision, and the probability of this is called the power of the test. Now, there's some important words here. Power of the test is kind of important, and type 1 and type 2 error are kind of important here as well. How do we keep a type 1 error and a type 2 error straight, knowing which is which? Well, think about true and false. When we say true and false, we always say true or false. We don't say false or true. It's natural to say true or false. True always goes first. False always goes second. Look at our definitions here. Null hypothesis true is type 1. Null hypothesis false, type 2. Null hypothesis is true, making a bad decision leads to a type 1 error. True comes first, type 1 error. Null hypothesis is false, making an incorrect decision. How we get a type 2 error because false comes second. So that's just a little way to maybe help you remember which is which, because those are important key terms that I would expect you to know. Now, I would want you to kind of think about the probability of a type 1 error and the probability of a type 2 error. Probability of a type 1 error we would call alpha. The probability of a type 2 error we would call beta. And we're going to look a little bit more at alpha than we will at beta. But it's interesting to know that the power of the test is related to beta. The power of the test is 1 minus beta. Now, ideally, we want the power of the test to be as high as possible. In order to increase the power of the test, we have to increase our sample size. And that's the only way that we can increase the power of the test. Now, as the power of the test goes up, the probability of our type 2 error goes down, and we want our error probabilities to be fairly low. Now, how do we make alpha, or probability of type 1 error, small? Well, we're able to choose our value for alpha. It's equal to 1 minus the confidence level. So this is also known as your level of significance. So choosing a very small value for alpha or a high confidence level, that's going to give you a smaller probability for a type 1 error. So by increasing your sample size and increasing the confidence level, we decrease the probability of an error in our hypothesis test. Now, as we're going through, we have a few different distributions that we can look at, and we're actually going to see this the same distributions that we looked at in our previous chapter. So we have our student t distribution that's used when we do not know the population standard deviation, when we have to assume that it's approximately normal population or that we had a large sample size. We have the normal distribution. It's used when we know the population standard deviation. We still need to assume an approximately normal population or large sample size. And it's also going to be used when we're testing proportions. So now we know a little bit about writing our hypotheses, figuring out which one is our claim. We know a little bit about, alpha and making sure that we choose alpha as something small. We kind of know how to select a distribution, and that distribution is going to help us find something called a test statistic. And that test statistic is going to kind of help us determine whether we're rejecting or not rejecting. To make that decision, we need to have some sort of rejection value or critical value based on regions in our pictures. So we've always drawn pictures so far, each chapter, when we're looking at probabilities and our inferential statistics so far. We've been tying things back to our central limit theorem, and hopefully we'll be able to kind of see the connection here as well. So a two-tailed test is going to look the most like what we've seen before. And so we have the mean centered in the middle, and then there's 2 bars. And if we're inside there, we're saying we're not rejecting the null hypothesis. If we're on the outside, then we're saying it's too far away. We're going to reject the null hypothesis. And this kind of makes us think of like our central limit theorem and our confidence intervals. With our confidence intervals, we're saying, oh, I'm 90% confident that's between these values. So it's outside of those 2 values that you just listed, then you're saying it's too far away. I don't think it's that. That's essentially what we're doing here, only we're looking at it a slight different way. We're saying, okay, let's calculate that value and then keeping everything standardized. Are we close enough to say do not reject the null hypothesis, or are we far enough away to say reject the null hypothesis? Now, with a left-tailed test and a right-tailed test, we only have one tail that has some sort of critical value that we have for a cutoff. But whenever you're in the tail area, you're rejecting the null hypothesis. Whenever you're not in the tail area, you're not rejecting the null hypothesis. And these red lines, these critical region cutoff values, we're going to call critical values, we're going to find based on our distribution. So if we're using the standard normal distribution, these are going to be z values. If we're using the student t distribution, these are going to be t values. So there's going to be some sort of value that separates the critical region from the non-critical region. And this value is known as our critical value. And the critical region is determined by our level of significance that you select. Remember, level of significance is alpha. It's equal to 1 minus your confidence level. The level of significance alpha is the area in the critical regions, the area in your tail. That gives you a nice little visual here of what we're talking about when we're saying this is your level of significance, your alpha value. It's how big of tail are you willing to allow? And remember that that's where you're going to have errors occurring, is in that tail. So we want to make sure that we're selecting a fairly small value for alpha so that we have a fairly small probability of error. So we found z values and t values before, and those are what we're going to be using for our critical values. And, you know, we found them based on having the area that's to the left of our line, and if needed, the sample size or degrees of freedom as well. And we're going to be using these same methods for finding our critical values. And we're going to be making sure that we're using the distribution that we're using for the test. So if we have population standard deviation, then we're going to use the standard normal distribution. If we do not have population standard deviation, then we would use the student t distribution. And if we're working with proportions, we're going to use the standard normal distribution. And these three pictures here can be a little bit useful for when we're trying to go through and say, okay, what value do I need to make sure that I have for area to the left when I go about trying to figure out what my critical value is? One thing to keep in mind for our two-tailed test is that our two critical values will have the same absolute value. So one is going to be a negative value, one's going to be a positive value, but otherwise they're equivalent. Now, we have 5 basic steps for completing the actual hypothesis test. And as you're going through your homework, you're going to see that I have it kind of broke down into these 5 different steps. So the first step is stating your hypothesis and identifying your claim. Your claim is whatever you're being asked to test to see if it's accurate. And remember, your null hypothesis should always contain an equal sign. Second thing you're going to do is you're going to select your level of significance, and you're going to find that critical value. That critical value is based on the distribution that you are using. Your critical value is what's going to help you determine whether you're going to reject or not reject the null hypothesis based on a test value that you calculate in step 3. So in step 3, you're finding a test value. This test value will be found based on a distribution that you select. We haven't discussed how to find these test values just yet. We're about to do that, but that depends on your distribution. Step 4, you're making your decision. So you're making your decision by comparing your test value to the critical value. Your decision is always going to be either reject the null hypothesis or do not reject the null hypothesis. You can always look at your picture to help you determine whether you are rejecting or not rejecting your null hypothesis. And then you're writing your sentence to summarize your results, and your final conclusion sentence we're going to go over on this next slide, how to write that. And then from there on out, it'll be, here is how you calculate your test value for this test, for this distribution. And then we go through do the process. Then we have, okay, well, what if it's this distribution? Here's how you calculate your test value, and you continue on. So we already know how to do steps 1 and 2. And we know how to do step 4 based on the pictures. Step 5, I'm going to give you on this next slide. Then step 3 changes based on each and every single test. So your conclusion sentence, you can use this slide as kind of a cheat sheet for how to write it. So it's based on your claim. You're always writing it about your claim, and then your decision also impacts how you write it. So if your decision is to reject the null hypothesis and your claim is the null hypothesis, then you would write there is enough evidence to reject the claim. You would want to go ahead and fill in your sentence what the claim actually is. If you decided to not reject the null hypothesis, then you would say there's not enough evidence to reject the claim. Now, if your claim was the alternative hypothesis instead of the null hypothesis, then we change just a little bit in our sentence here. So what we're changing in our sentence is instead of saying reject, we're going to be saying support. So notice that whenever our claim is the null hypothesis, we're saying reject. And if the claim is the alternative hypothesis, we're using the word support. And the other thing that we make note of if we're saying do not reject, we're using the word not in there. When we're using the word reject, we don't have the word not in our sentence. So there's just some things to keep in mind. I would highly recommend writing this down somewhere where it's handy to reference, because you will be using this format for writing your sentences for all the rest of the hypothesis tests that we do this semester, which hypothesis testing is chapter 9 through 11, 9 through 13. 13 chapters that we cover. So chapter 9, 10, 11, 12, and 13, all 5 of those chapters we are doing hypothesis testing. So let's talk about using the standard normal distributions. This is where we know the population standard deviation. We are going to find our test value based on this. The sample mean minus mu naught divided by our standard deviation, where mu naught is equal to the mean of our data values and sigma is equal to the standard deviation of your data values over the square root of n. So basically we're using the same things that we had from our central limit theorem. Now our critical values, we're using our normal distribution. So we would be saying inverse norm, area to the left, the 0, then 1. So let's do an example. Here we have Jeff as an 8-year-old. He has an established mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad, Frank, thought that Jeffrey could swim the freestyle faster using goggles. So Frank bought Jeffrey an expensive pair of goggles. Wearing these goggles, Jeffrey swam the 25-yard freestyle 15 times. For these 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles definitely helped Jeffrey swim faster. Conduct a hypothesis test to see if Frank was statistically correct. Use the level of significance of 0.05. Assume that these times for the 25-yard freestyle are approximately normal. All right, so whenever we read through a problem like this, there's a lot going on. So we always want to say, okay, what are the important bits of information? And one of the most important things is, what is the claim? What claim is going on here? So the claim is that the new time is faster or less than the previously established mean. Now, your previously established mean is what we're comparing to. So that's going to be your population sample mean, what you're comparing to in your hypotheses. And then we also want to make sure that we identify, okay, what is the population standard deviation? What is our sample mean? What is our sample size? And we also probably should make note of what level of significance that we wanted to use. So one thing I didn't have typed out already was alpha. But I have it here as we carry things forward to the next slide so that we can do our hypothesis test. So let's begin our hypothesis testing. Step 1, we need to write our hypotheses. So writing our hypotheses, we're comparing mean to our previously established mean of 16.43. The claim is that we're faster, so that the time is less than previously established mean. So we would have this set of hypotheses. Then we would say, okay, well, what's my level of significance, or what's alpha? And then use that as we find our critical value. And find your critical value. Remember that you're going to have to pay attention to if you have a left-tailed test, right-tailed test, or two-tailed test. But then we can go ahead and fill this information in on a picture to help us visualize things. From there, step 3, we're going to be finding our test values. We're going to be taking our sample mean minus our previously established mean time divided by our standard deviation over the square root of the sample size. So we're going to get that our test value is negative 2.08. We'll draw that into our picture as well. And then we say, okay, am I in the tail area or am I not in the tail area? If you are in the tail area, you reject the null hypothesis. If you're not in the tail area, you do not reject the null hypothesis. Looking here, the test value is in the tail area beyond our red line of the critical value. So we'd say reject the null hypothesis. Therefore, there is enough evidence to support the claim that the goggles made Jeffrey faster. All right, one hypothesis test down. We've done it by hand. We're going to continue to do things by hand using our formulas. And at the very end, I'm going to show you the calculator on this. So don't panic if you're like, oh my goodness, these calculations are rough. We're going to get there, okay? Hold on for just a minute. So if I use the student t-distribution instead, I'm going to use a very slightly different formula. The only real change here is that I'm using the sample standard deviation instead of the population standard deviation. And for my critical value, I'm using the inverse t function instead of using the inverse norm function. So here we have students that believe the mean score on the first statistics test is a 65. And the statistics instructor thinks the mean exam score is higher. He samples 10 statistics students and obtains scores of 65, 65, 70, 69, 66, 63, 63, 68, 72, 71. He performs a hypothesis test using a 5% level of significance. The data are assumed to be from a normal distribution. So what's our important bits of information? Well, first off, what's our claim? Our claim is the mean score is higher than or greater than 65. We also know that we're going to be using the student t-distribution because we do not have the population standard deviation. And we know that we need to find the sample mean and the sample standard deviation in order to use our calculations here. So we go ahead and calculate the sample mean and the sample standard deviation. You can pause this, give yourself time to calculate them, that we are practicing going through this. X bar is 67, S is 3.1972. Degrees of freedom is 1 less than your sample size, so degrees of freedom is 9. Your sample size here was 10, and then your level significance was 0.05. So carrying that forward to our next slide, we're able to begin our hypothesis testing. Our hypotheses, we'd be saying the null hypothesis, the mean is less than or equal to 65. Alternative hypothesis, which is our claim, is the mean is greater than 65. We know that alpha is 0.05. We use inverse t to come up with our critical value. Our critical value is 1.833. We draw it into our picture, and then we can find our test value. Our test value, we're taking our sample mean minus the previously claimed mean, and then dividing it by the standard deviation over the square root of the sample size. And we're getting 1.978. So we draw that into our picture. We see that's out into the tail area. Since it's in the tail area, we know that we should reject the null hypothesis. Since we're rejecting the null hypothesis and our claim was the alternative hypothesis, we're saying there is enough evidence to support the claim that the test scores are higher than 65%. All right, so what if I'm doing hypothesis testing for proportions? Well, doing hypothesis testing for proportions, my z value is going to be p hat minus p naught, the value that you're comparing to in your hypothesis. And then you're dividing by p naught times 1 minus p naught divided by n, and you're taking the square root of that denominator there. Now we're in this standard normal distribution, so you'd be using inverse norm for your critical value. So here in our example, we have June. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same as 50%. She samples 100 first-time brides. And 53% reply that they are young. 53 of the 100 reply that they are younger than their grooms. For the hypothesis test, she uses a 1% level of significance. So what's our important bits of information? Well, she's claiming that the proportion is equal to 0.5. We should calculate our p hat here. P hat is 0.53. Our p naught, what we're comparing to, is 0.5. N is 100, and alpha here is 0.01. So we write our hypotheses, and here we notice that our claim ends up being our null hypothesis because we're claiming that we are equal to 0.5. Then we go ahead, we find our level of significance, state our level of significance, and we find our two critical values. This here is a two-tailed test. So we're going to find our critical values of negative 2.58 and positive 2.58. And then we calculate our test value. So we're doing p hat minus p naught divided by p naught times 1 minus p naught over 100. Square root of that denominator, and we get 0.6. So our z value is right there in the middle. It is not in the tail area, so we do not reject the null hypothesis. Since we do not reject the null hypothesis, we say there is not enough evidence to reject since the claim is the null hypothesis, we say reject the claim, and that the proportion of brides that are younger than their grooms is equal to 0.5. Now, this is going through this whole testing process using what's called the traditional method. Now, you do not have to use the traditional method when you're going through doing your hypothesis testing. In fact, there's another method that most students tend to use instead. But again, I like showing you the long way first, so you kind of have an understanding, a grasp, and an appreciation for the material that we're working on. And also it helps us to see the connections between a little bit better. But we can also do this using the p-value method. And the p-value method requires us to use our calculator. So the steps for completing it are going to look pretty much the same. Step 1 is exactly the same, stating your hypothesis, identifying your claims. Step 2, you're just selecting a value for your level of significance. So you're only stating alpha here. Previously, we were stating alpha in your critical value. Now we don't need the critical value, we just need alpha. Now, in step 3, though, we need a little bit more than just the test value. Before, we just had the test value. Now we have the test value, and we need to find the p-value. The p-value is found based on your distribution, just like your test value was, and you're going to need your calculator for calculating the p-value. Step 4, you're still making your decision. You're making a decision by comparing your level of significance to the p-value here. So before, we were using our test value and our critical value. Now we can use alpha and p. The decision is still always reject the null hypothesis or do not reject the null hypothesis. If we have the alpha is less than p, we decide do not reject the null hypothesis. If we have the alpha is anything greater than or equal to p, then we would reject the null hypothesis. And then step 5 is the same as always. Write a sentence summarizing the results. Now, for finding p-values, you can use tables or you can use the calculator to find p-values. What is a p-value? A p-value is a probability of being in the tail area beyond the test value that you calculated. I honestly think that we've done plenty of doing things by hand, especially in this chapter. So I'm not going to make you do this by hand. So I would encourage you to go ahead and use your calculator. If you have questions about how to do this by hand, feel free to contact me and ask me questions. I'd be more than happy to discuss it. I just don't want to bog down the entire class when I have a hunch that most of you want to just use your calculator anyway. So let's go ahead and grab our calculators and talk about calculator functions that are going to get us these p-values. Remember, p-values are probabilities. Probabilities are always between 0 and 1, so we're going to have to make sure that we think, because our calculator is going to have this nasty habit of giving us things in scientific notation, and scientific notation is going to make it look like a p-value is bigger than 1. P-values can never be bigger than 1, so keep that in mind as we use our calculator functions. So we're going to go to stat and then over to test, and then we're going to find the following functions. The z-test, which is used for the standard normal distribution tests about means. The t-tests for our student t distribution test about means, and the one prop z-test, the normal distribution test about proportions. So in order to go through these and practice these three functions here, we want to make sure that we know that they're working well. So we're going to compare them to the examples that we just did, only using the p-value method. So we're going to redo our previous three examples, and this time we're going to use the p-value method. So we're redoing our examples here, and I'm not going to read through it because we've read through this in this video, but this is our example with Jeff. And what we're going to do here is we're going to take a look at the important bits of information. The important bits of information was the claim is that the new time is faster than or less than the previously established mean. And we found the previously established mean was 16.43, standard deviation was 0.8, the sample mean was 16, and our sample size was 15, and our level of significance alpha was 0.05. So we write our hypotheses, same exact hypotheses that we had before. Step 2 looks a little different because all we're doing is we're writing alpha is equal to 0.05. And then we find our test value and p-value. And we're finding these by going to the z-test on our calculator and typing in the correct information. So mu naught is what we have written in our hypotheses. So that's the 16.43. Sigma is our standard deviation, so 0.8. X bar is our sample mean, so 16, and then n is our sample size, so 15. And then it's going to ask us about a symbol. We always want to make sure that we select the symbol that is in the alternative hypothesis. So we're going to select the less than symbol to make sure that it matches the alternative hypothesis. When we do this, we should get this test value and p-value that I have on the screen here. Now, to make our decision, what we're going to do is we're going to compare alpha and p. Now, comparing alpha and p, we see that alpha is bigger than p. Whenever alpha is bigger than p, we're going to reject the null hypothesis. So since we rejected the null hypothesis, we would say that there is enough evidence to support the claim the goggles made Jeffrey faster. So everything about our entire test stayed the same except for step 2 and step 3. Step 2 got shorter, step 3 got longer. Okay, let's run through our second example that we did, where we had our statistics students that believed the mean scores and the test was a 65, and the instructor said, no, I think it's more. Okay, so what was our important bits of information? We claimed that the mean is higher than, greater than 65. And we said we're using the student t-distribution. And since we want the p-value, we're going to use our calculator. So instead of finding the sample mean, the sample standard deviation and everything, we're just going to put all the data values into a list on our calculator to help perform this test. And do make note that the level of significance is 0.05, and the degrees of freedom is 9. So we're going to need to know that we have all of our data in our list. And we're going to need to have that we're comparing to 65, our degrees of freedom is 9, and our alpha is 0.05. So those are going to be important things to keep in mind. We write our hypotheses, exact same hypotheses as we wrote before. Step 2, alpha is exactly what we had for alpha before. We're just not listing our critical value now. Step 3, we're going to use our calculator to come up with our test value and our p-value. So we're going to stat over to test. We're using the t-test. We're telling it that we have data. We're saying that we're comparing to 65 and that our alternative hypothesis has a greater than symbol. So we're going through selecting all of those things, and then we're getting these values. Test value of 1.978 and a p-value of 0.040. Here we see that alpha is greater than p. So we reject the null hypothesis, which means there is enough evidence to support the claim that the test scores are higher than 65%. Again, this is exactly what we had done before when we did things by hand, except for step 2 got shorter, step 3 got a little bit longer. Okay, one more example, and then we'll talk about some of our limitations. So we have June that believed that 50% of first-time brides were younger than their grooms, and she had collected her data. She said, okay, 53 were younger of the 100 that I sampled, and I want a 0.01 level of significance. So we figured out our claim, kind of wrote down our important bits of information that we might need for our calculator, and then we're going to go ahead and start our hypothesis testing. So we have our hypotheses, exactly what we had before. And then we have alpha written down for our step 2. And then we want to use the 1propz int function in our calculator. And for this, we want to plug in what x is and what n is. And so instead of looking at the p hat here, instead of that, we're really thinking about x. X is equal to 53, and then we're also needing n. So we need x and n, and then helps if I'm looking at the correct test on my calculator here. So we need x and n, and then we're also needing p naught. So those are the things that you're needing in your calculator. And then of course, selecting the correct symbol, and you will get your test value, your p-value. Now here we see that alpha is less than the p-value. And when alpha is less than the p-value, we do not reject the null hypothesis, which means there's not enough evidence to reject the claim the proportion of brides that are younger than their groom is equal to 50% or 0.5. All right, so that's a quick rundown of how to do things in the calculator. If you have questions, it's absolutely okay. That's totally normal. Make sure that you email me with any questions that you have, and I'd be more than happy to walk you through how to do things 1 more time, 2 more times, however many more times that you need it. And we can meet on Zoom if you need it. But just please make sure that you're emailing me if you have questions for us to go through it. Just one more thing before we finish the video, we need to talk about assumptions and limitations. What assumptions are we making? What limitations do we have when we're doing these tests? So for each one of these tests, we're relying on the assumptions from the central limit theorem. So we want to make sure that we're being aware that the assumptions of the central limit theorem have to be met in order for the test to hold. There's always a chance of error, and we can only do so much to limit that error. So the larger the sample, the smaller the probability of an error, and also the smaller the value for alpha, the smaller the probability of an error. We are at this point limited to just when we can assume the central limit theorem applies. And if those assumptions do not hold, then our test does not hold. And right now we're just looking at a data value or a statistic compared to a number, testing to see if that's correct or not. We're not able to compare 2 parameters to each other at this point. We're going to get there in the next couple chapters. But right now we're just saying, okay, is this parameter equal to this, not equal to this? Is it greater than this, less than this, greater than equal to this, less than equal to this? That's where we're limited to at this point. So there's not tons that we can test. There's quite a few different ways that we can see how we can apply it. But so that is chapter 9. And that wraps up our second unit. So after this, after you've got your homeworks done, then you can start preparing for your next test. And of course, if you have questions, do make sure that you email me.